Welcome back, everybody. So we are going to finish off 2.5 today and then start up 2.6. Maybe even if we're lucky, finish 2.6. But we'll get there when we get there. So last time we talked about logarithmic differentiation and how to use it. So you apply the natural log to both sides, and then you differentiate. So the main goal is to do it on things that like someone asked me in the other class, well, actually, let's wait until we're done with the next one before I mention those things. So these things here are ones that can only be done with logarithmic differentiation. So like, yes, the previous two problems would have been tedious, but we could have done them without logarithmic differentiation. But this one right here cannot be done. There is a way, and I'll mention it, but I highly recommend not doing that way. It's a really weird trick. But John Doe student, so don't write this down. John Doe student decides, oh, well, that's easy. Y prime will just equal x times x squared plus 1 to the x minus 1. Done deal. Oh, and then, of course, don't forget the chain rule. So why is John Doe student wrong? Power rule. I forgot to write it here, but the power rule should say for any number n. So the power rule only works for finite numbers, for finite exponents. The problem here is that x squared plus 1, the x is a variable. So it changes with time. It changes as x changes. So the power rule does not apply here because x is not a finite number. It's a variable. So what we have to do instead is we apply the natural log. And so you get the natural log of the left-hand side equals natural log of the right-hand side. That is natural log of y is equal to natural log of x squared plus 1 to the x. And I know what you're thinking, well, Phil, that just made it more complicated. Now I've got natural logs in it. But we got to remember one of the most important properties of logarithms is that they can take care of exponents. This exponent right here can be brought out front. Now that we're dealing with a logarithm, we can bring the exponent out front. So in particular, we have that this is equal to x times natural log of x squared plus 1. So that is something we can differentiate because that's a product of two things that don't have that are nice. So now we have to differentiate with respect to x. Left-hand side, natural log of y, the derivative of that would be 1 over y times y prime, or 1 over y times dy dx, equals, here we've got a chain rule. We got f prime, or not chain rule. Well, we do have a chain rule, but it's more than that. It's a product rule with a chain rule inside. So f prime g plus g prime f, that'd be 1 natural log of x squared plus 1 plus the derivative of g. So the derivative of natural log of x squared plus 1, so that'd be 1 over x squared plus 1 times 2x times f, that'd be times x. And at the end of the day, in order to solve for dy dx, we have to multiply both sides by y. So dy dx is equal to, but remember here, y is equal to x squared plus 1 to the x. So just like with logarithm differentiation, we rewrite y as what it is. Y from the original problem statement is x squared plus 1 to the x. So to make this look pretty, x squared plus 1 to the x times natural log of x squared plus 1 plus 2x squared over x squared plus 1. And that is our answer. So this can only be done with logarithmic differentiation or by doing a very, very roundabout trick. So I'm going to show you the alternative option just in case you're curious, because it is a nifty little trick that some mathematicians like to use. Alternative option is that x squared plus 1 to the x. Well, what we could do if we were so inclined, if we were so clever that we're like, you know what, technically this is true. You could rewrite this as e to the ln of x squared plus 1 to the x. Because e and ln are inverses of each other, so they cancel each other out. So really, it's kind of like multiplying by 1. It doesn't do anything. So by adding an e and then an ln, it doesn't actually do anything. But then, of course, we can bring the exponent out front and get that this is e to the x times ln of x squared plus 1. And then you have to do a chain rule with a product rule on the inside. And it ends up working out just as well. But since you can use logarithmic differentiation in 2 different ways, might as well use it that way. Might as well learn this way instead of the alternative option. Granted, if you want to do that way, you're more than welcome to. It's completely valid, but I wouldn't. So let's do it again as another practice. So this time f of x is equal to the natural log of x, the sine of x squared. Let's add a little bit extra spice to it. And so we're going to write this as y just to make things easier and apply ln. And just like with the ddx thing on each side of an implicit differentiation or all that stuff, you don't need to write this step. You can just write it down. It's just for our notes. So natural log of y is equal to natural log of bracket natural log to the sine of x squared, which we will just rewrite as that sine of x squared times natural log of x. That's okay. It's weird, I know. Weird, I know, but natural log can be put inside a natural log. You could have natural log of natural log of natural log. Who cares? You do it as many times as you want. So let's go ahead and differentiate that on both sides. I'd like you to do that and check your work with me. And we'll go in big here. I have the answer on the for if you'd like to check your work, but if you're still working, you need to do so. So the derivative of sine of x squared, outermost function is sine, so cosine of the inside, so cosine of x squared times the derivative of the inside, so 2x times natural log of x, because that's f prime g equals g prime f. G prime, so the outermost function is natural log, so 1 over the inside, so 1 over natural log of x, because that's the inside, and then the derivative of the inside, which would be 1 over x, then times f, so that And then we're going to multiply both sides by y. That it cancels on the left, and we get our final answer, which is the dy dx, which we're actually going to rewrite now as f prime, is equal to ln of x to the sine of x squared times 2x cosine of x squared times natural log of x plus sine of x squared over x times ln of x. All righty. Cool. Any questions on that? By the way, guys, once again, I'm sorry, my energy's at kind of at a lower level today. It's not, and so I'm not at like, please feel free to ask questions. I know I sound kind of intimidating right now or pissed off, but I'm not. I'm just a little slow today. Cool. Totes chill. Johnson, no tears. Right. Okay. So one thing that the student asked, and I want to add it to my notes. Like, did I make a note to myself to make a note? No. So just for my own sanity. So when to use logarithmic differentiation? So when should you use this process? Number one, like the thing we just saw, which or the thing we previously saw last time, which was insane amount of product / quotient rules. As an example of this, let's say your function was y equals x squared plus 1 to the third times x minus 9 to the seventh times e to the x plus 8 divided by uh 2x minus 5 to the 1/3 times 3x plus x squared to the 10th. That would be a situation where I'd look at that and I'd be like, please don't make me. Like, if you're looking at a derivative and you go, I don't want to do that, which maybe that is for every derivative for you, but specifically for this one, if you're looking at it, it's like, no. I don't want to do that. That'd probably be a good indication of using logarithmic differentiation. If there's a lot of pieces, like if you see like multiple product rules and quotient rules, that would be a good option for logarithmic differentiation. And the other one is for a function raised to a function. So for example, something like what we just saw previously. So y equals x to the x, g of x equals cosine of x plus 1 to the e to the x, and so on and so forth, things like that. So if you have a function raised to a function, you kind of have to do logarithmic differentiation. But if you have like, if you really want to go through the motions, you can definitely find the derivative of that. You'll need to turn your paper landscape wise. That's going to take a lot of writing, but you can do it. But logarithmic differentiation will make that a little bit easier, especially as you get comfortable like skipping the steps. We're showing all the nitty-gritty details here, but if you want to go straight, like you don't have to write apply ln. You could write this and then take the derivative and not write the multiplying by y or anything like that, not writing the differentiate with respect to x, and just go straight to it, and that would be fine. So that is when we use logarithmic differentiation, is if you have large amounts of product motion rules, or if you have a function raised to a function. So last little thing from section 2.5, talking about how to find horizontal and vertical tangent lines for implicit differentiation. So I'm going to scroll back for a second. I want you to notice something for everything previously. Quotient. This is a quotient of two things. Like it's a fraction. The derivative was a fraction. Derivative was a fraction. dy dx 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 was a fraction. And finally, dy dx was a fraction. Pretty much every situation with with implicit differentiation ends up being a quotient of two of things. So usually you get something like stuff over things. Very scientific, I know. And thing is, if you're trying to find horizontal tangent lines, that would be when the derivative is equal to 0, because that would a horizontal tangent line would have a slope of 0, and the slope comes from the derivative. So the derivative equaling 0. Now, the only way for the derivative to equal 0 is if the numerator equals 0. If the denominator equals 0, that's a different situation. So we have horizontal tan lines if stuff equals 0. And then if the denominator, if the things are equal to 0, that would mean we're dividing by 0. And what we've learned is that means you have an undefined slope, right? If you have a finite run over an infinite rise, that's an undefined slope. That's like if you, when you're doing the rise over the run, right? If you have some number up top, but you don't go anywhere, that's going to give you a vertical line. So in the same fashion, when your things, your denominator equals 0, you will have vertical tangent lines. So vertical tangent line if the things equals 0. Now, in case there's any secret math teachers out there who are trying to catch me off guard, I know, technically speaking, this is not 100% true, because if it ends up being that it's a factor of both the numerator and the denominator, if the x or y values end up making both the numerator and the denominator 0, then some wonky stuff can happen. So remember, these are curves. They're not functions, so they can be anything we want. You could have something like this. You don't need to draw this. This is just for reference, just to give you an idea of some interesting things that can happen. Let's say your curve looks something like this. And like that. So if you like, that's not a function, that's a curve, but you'll notice that at this point right here, there's a vertical tangent line and there's a horizontal tangent line. So when you get one of those situations, it's hard to tell what you've got when it becomes a factor of both the numerator and the denominator. So if like both pieces become 0, you get 0 over 0. And if you remember what we talked about, that's indeterminate. So number over 0, that is undefined. That is an undefined slope. But 0 over 0 is indeterminate. It could be 1, it could be 5 billion, as we saw with limits. If you had x squared minus 25 over x plus 5, you got 0 over 0 originally, and then you factored and canceled, you got an actual number. So in those situations, you have to do a little more work. Now, what I will tell you is that for our class, we're going to avoid those situations because those are very, very nuanced and not really useful for this course. But suffice it to say that there is some gray area here. So, but everything that I present to you, if there's ever a problem on your homework or on a quiz or an exam that involves trying to find where there's vertical tangent lines and horizontal tangent lines of a curve and not a function, I will make sure that that situation does not occur. So find all the points, possibly points where the curve represented by the equation 9x squared plus y squared minus 18x plus 6y plus 9 equals 0 has vertical and horizontal tangent lines. Does anybody know what that curve is off the top of their head? I'll give you a hint. You encountered it in Math 127 in trig. Yeah. It was in the conic sections. Because it has a coefficient here, it's x squared and plus a y squared. That's an ellipse. I can't remember what type of, like, just because I don't have it in the right format for my brain to think about it. But you're either going to have this or you're going to have this. And so the reason why I mention that is this helps us narrow things down. This means we should have 2 horizontal tangent lines and we should have 2 vertical tangent lines. So if we don't get 2 of each, we know we did something wrong. That's the reason why I bring that up. So first things first, d dx of both sides, because we need to find dy dx. So d dx of 9x squared plus y squared minus 18x plus 6y plus 9 equals d dx of 0. We're taking the derivative with respect to x. So the derivative of 9x squared would be 18x. The derivative of y squared would be 2y dy dx. Derivative of 18x would be 18. Derivative of 6y would be 6 dy dx equals 0, because the derivative of 9 and derivative of 0 are both 0. All righty. Then we'll bring everything over to one side. I'm going to get you, I want to show you how you can do it quickly in your head, but you can, like, so you can save yourself some algebra, but I will write the other step. So the answer should be not the answer, but the derivative should be 18 minus 18x divided by 2y plus 6. See if you can figure out how I got there. It's okay if you can't, because I'm going to show the next step, but I want, like, I'm just trying to push you a little bit on your mental math skills. So once again, the core thing that you want to do with an implicit differentiation problem is once you differentiate both sides of the equation, isolate the dy dx terms. So on the left-hand side, we have that 2y plus that 6 times the dy dx. And then I brought the 18 over and by adding it, and I subtracted the 18x. Now we can simplify it if we want to, but we're really just going to be setting them equal to 0. So let's go ahead, and we've got plenty of space to work with, but let's do horizontal first. I'm going to do that up here. Horizontal first. We're going to set 18 minus 18x equal to 0, and that gives us x equals 1. Because you'll subtract 18 from both sides, divide by negative 18, you get 1. Okay. The John Doe student boxes this as their answer. And once again, John Doe is not right. Why is John Doe not right? Well, yes. I should have clarified. That is not one of the answers because that is an x value. Just an x value. It wants the points. But wait a minute. I can't plug it into a function. Yes, I can. I can plug it into the equation. What an equation is it's a set of all the points that satisfy that. So if we know this is the x value that satisfies this equation, we can plug it in and solve for y, hopefully. Sometimes you can, sometimes you can't. For everything that we'll encounter, there will be a way. So to find y, plug in to original equation and solve for y. So plug it in. Oh, geez. The denominator 0. So great question. Can we not just set the denominator equal to 0? That is going to give us a completely separate piece. That'll give us where we have vertical tangent lines. So notice that up in the numerator, we only have x's, and down in the denominator, we only have y's. So we found that when x is equal to 1, we have horizontal tangent lines, when y is equal to -3, that will give us vertical tangent lines. So they're going to be separate from that thing. Great question.
Will finding the differential always lead to all x's on top and all y's on the bottom?
Not always. For us, like, it gets a lot more complicated if that's not the case, especially I mean, there's entire math classes upper division that talk about trying to factor multi-variable polynomials, which it's a daunting task. It takes a little bit of time to get comfortable doing that, especially trying to do long division with multiple variables. It's not very fun. I mean, I think it's fun, but then again, that's me. But for everything that we'll be dealing with, I'm going to try and make sure that it is nice enough. Once you start incorporating other things, it becomes a little bit harder. If it would be that case, if there would be ever a situation, I would make sure that it would factor nicely and be very apparent. Like maybe it would be like 18, at most it would be like 18y minus 18xy. So there's like a common factor y can just be brought out front, done deal. Not something like 18y squared plus x squared minus 18xy plus 9y. That's a lot to ask for. That's a tall order. So, of course, great question. Very, very good question. So plugging in 1 into the equation, the original equation, 9 times 1 squared. I'll write it down, but you can just plug it in. 9 plus y squared minus 18 times 1 plus 6y plus 9 equals 0. That gives me y squared plus 6y equals 0. Because you get 9 minus 18, that's -9 plus 9, that would be 0. And so that gives us, we can factor it or we can solve it right off the bat. The solutions should be y equals 0 and -6. But the reason for that is you factor out a common factor of y. And so you solve for it. You got 0 and -6. So this is a good problem. I bring this one up for a lot of reasons. It's not going to come up until Math 283. But in Math 283, just in case, just to pique your interest a little bit, instead of having f of x, you start having functions f of x, y. And so you have what we call partial derivatives, a derivative with respect to x and a derivative with respect to y. And in order to find we'll get to it eventually, but we start having to solve for critical values. We'll talk about that in Unit 3. But usually in 283, when you solve those equations, you end up finding like one x value and you have to find the corresponding y values. Potentially one y value, potentially more. So this is a good thing to practice for later on. I mean, 2 semesters from now. But so with that one x value, we got 2 y values. So that means we have 2 different distinct points. We have 1, 0 and 1, -6. The x value is the same. For the x value 1, we got 2 different y values. So we get 2 points that have the same x value. That is okay, especially if we remember our picture. So if you have if you have an ellipse, doesn't matter which orientation, notice that the horizontal tangent lines, they have the exact same x value. Their y values are different, but the x, like the where they occur on the ellipse is the exact same x value. So that's the reason why it's okay. So that is the horizontal ones. We'll box that in. And then we'll do vertical. So vertical, we set the denominator equal to 0, 2y plus 6 equal to 0. That gives us y equals -3. And in the same fashion, we're going to plug it into the original equation to find the corresponding x values that will satisfy our ellipse. So 9x squared plus negative 3 squared minus 18x plus 6 times negative 3 plus 9 equals 0. That gives us 9x squared plus 9 minus 18 plus 9. So it's 9x squared minus 18x equals 0. Right? Yeah. And so the solution will be x equals 0 and 2. But to verify that to you, factor in a 9x. That's where I got those two answers. I'm showing this mainly because I want you to know that you can skip some algebra if you want. You don't have to factor it, like go through all the factoring yet.
How do we know we're setting it to 0?
So excellent question. Excellent question. How do we know we're setting it equal to 0? We're not. The original equation had the right-hand side equaling 0. So that I'm glad you bring that up. That just was happenstance. It could have just as easily been that this was equals -9, and then it would be equal to -9, and you would solve that way. Great question. Actually, that's a very, very good argument for me to change that to make it equal to -9. Or maybe not. So we make sure to bring that up. So it's not necessarily that we're setting it equal to 0. It just so happens the right-hand side was equal to 0. So we got 2 x values for our 1 y value. That means we have the point 0, -3 and 2, -3. Remember, in this case, the y value is the same. So it's either x equals 0, y equals -3, or x equals 2 and y equals -3. So those are your vertical and your horizontal. Vert and horizontal. Yes.
The vertical of the y x plug into the original function.
Yes, into the original function, just like before. Yes. Because we're trying, and I'm glad you bring that up. The reason we're doing that, the reason why we're plugging it into the original equation is, remember, we're finding tangent lines to the original equation. So if we found the x value, we want the corresponding y value that solves the equation. It's a point on the curve. It's one of those things that's not really mentioned very, very often, but when you see a circle, x squared plus y squared equals 1, what this is saying is all the points that satisfy that equation. So 1, 0 is such a point, 0, 1 is such a point. It's all those points. So we find a y value and then we find the corresponding x values. All right. Very, very fun problem at the question number 6. I gave you the picture to help you figure out how to figure this out. It has strong correlations to this problem. I felt really, really cool when I made this problem up. So highly recommend. Anyways, so that finishes 2.5. Are there any other questions on the horizontal and vertical tangent line stuff? All right. So a brief review of inverse functions. So a function has an inverse if and only if it is 1-to-1. I hate that terminology. I hate using the term 1-to-1. In fact, I'm going to be that petty, and I'm going to change this to the real way to say that a function is 1-to-1, which is injective. Don't actually cancel it out. Don't I just want to complain every time I see it, because 1-to-1 actually can mean 2 different things. And for whatever reason, mathematicians thought that was okay. The real way to say it is injectivity, and then there's surjectivity, and there's bijectivity. But anyways, this just also makes you sound cooler. That's an injective function. But anyways, that's not really super important to what we're going to be talking about now, right now. But inverses require that when you compose them, F composed of G or G composed of F, they equal exactly X. So typically the inverse is denoted F to the -1, which is not meant to mean the -1 power. That is meant to mean the inverse. And so, for trigonometric functions, we usually write either sine inverse like this, or we write like that, or we write arc sine. I typically write arc sine. I typically write sine inverse. I don't really like to write arc sine, but I can do that on exams if we would prefer. Do we have a preference of one over the other? Okay, so if inverse sine or inverse cosine or anything like shows up on an exam, I will make sure to mention on the board sine inverse means arc sine, or tangent inverse means, or like tan -1 means arc tan, but either way. So key point that is important when understanding inverse functions, that if a comma b is a point on the graph of f, then b comma a is a point on the graph of f inverse. That's how inverses work. The function takes an x value, gives you a y value. The inverse function undoes that. It takes the y value in and gives you the x value. So it has the opposite coordinates. And so written differently, which is useful for the inverse function theorem coming up, is that if f of a is equal to b, then f inverse of b is equal to a. That's another way to say the same thing. E and ln are inverses of each other, and then there's the graphs are symmetric to each other across the line y equals x. So don't write this. You don't need to draw this, but I'm gonna just do this funsies. Here's the line y equals x. And you'll see that if you have a function like this, if this blue line is your function, then your inverse function looks like this. So they don't share any common points. I mean, like they will intersect eventually, but they don't share any really common points, but they're symmetric. So that raises a question of whether or not there's some relationship between their tangent lines, between corresponding points. So like the tangent line at a comma b and the tangent line at negative or at b comma a, the flip point, the point on the inverse. So for a experimental problem, consider f of x equals x squared with domain 0 to positive infinity. If it was the whole real line, x squared looks like this, which is not 1 to 1. So that's why I've restricted it to one side. Find the inverse of the function. So if you remember, to solve it, you make y equal to x squared and you solve for x. So x equals plus or minus the square root of y, but we're going to choose the positive because domain is bracket 0 to positive infinity. That's not super important for you to know for this course, but when you take the square root of both sides, you'll get a plus or minus. But since x is positive, because our domain is 0 to positive infinity, that means we couldn't have the -1, otherwise problems would arise, like then it wouldn't be that piece. So we have that f inverse of x is the square root of x, which is x to the 1/2. So if that's the case, then f prime of x is 2x and f inverse prime of x is equal to 1/2 x to the -1/2, or preferably when we're computing 1/2 times the square root of x. That's the -1/2 power that puts it in the denominator, and then it's 1/2 power since it's the square root. So that's the derivative of f and the derivative of f inverse. They don't look super similar. I mean, like somewhat similar, but not anything that I would say like, oh, that's really cool and symmetric. But the graph of f has the point 2, 4. Right? If you plug in 2 into that function x squared, you get the y coordinate of 4. And as a result, the point 4, 2 is in the graph of F inverse. And so we're going to find the slopes of the tangent lines. F prime of 2 is 2 times 2, which is 4. And that's M, like that. That's your M tan for that, versus F inverse prime of 4, the point on the inverse graph, point on the inverse function, would be 1 over 2 times the square root of 4, which would be 1 over 2 times 2, or 1/4. Reciprocals. Was that a fluke? Is it just because Phil chose the points 2, 4, and 4, 2 that it worked out? Or is there something more going on here? The answer is there's something more going on here. I guarantee you, if you plug in 3, 9, you plug in 3 in for F and 9 in for F inverse's derivative, you will get 6 and 1/6, and so on and so forth. So that leads us to the inverse function theorem. Suppose F is a 1-to-1 function such that F of A is equal to B. And I'm going to underline that F of A is equal to B. If F is differentiable at A, then F inverse is differentiable at B. Because remember, A isn't necessarily going to be a point on F inverse. Now, A isn't going to necessarily be an X value of F inverse. But because A comma B is on the graph of F, B comma A, the X coordinate B, is on the graph of F inverse. Inverses are always hard to grasp, at least at first. So further, and this is the cool part, this is the really cool part, the inverse derivative evaluated B is equal to 1 over F prime of A. Which is pretty miraculous. That why is this important? Why do we care? Why do we care at all? Okay. Try and find the inverse of this function. Can you find the inverse of that function for me? Do you want to do that? No, it's impossible. It's straight up impossible to find the inverse function of that. So, but what happens in, whether it be contrived mathematically, like a ridiculous example, or something that's actually useful for the real world, what if you needed to find the inverse's derivative at a point? What if you needed to find the rate of change of the inverse? Speaking you can think of inverses do actually have important aspects in real world. I'm blanking on examples at the moment, so don't question me on that, but we all good with me? Believe in me that one? Awesome, cool. But the point is, if you can't find the inverse, you can't take its derivative. But we can take the derivative of this function. It's going to be tedious as all get out because it's 4 product rules. But you can find its derivative, plug in an A value, and you'll find the inverse's derivative. So that is a very, very unique point about this. It's very, very important in mathematics. Honestly, it's one of the more important theorems. For us, not so much, because it's a very, very theoretical thing, but it does help us in a lot of proofs later on in mathematics. And this is the single variable case of the inverse function theorem. There's actually a multivariable case, which I think I've told you guys about Rudin, Rudin's textbook. Principles of Mathematical Analysis by Walter Rudin. Don't write this down, but this textbook, I should have brought it today. I'm sorry. It's this big. It's this big and that thin. But it has the density of a dying star. It is Walter Rudin. He wrote this when he was in grad school. We call this Baby Rudin because he wrote it in grad school. And he wrote another book called Complex Analysis, which they call Papa Rudin. So Baby Rudin and Papa Rudin. But Baby Rudin is one that everyone studies. And one of the reasons why we mathematicians love his textbook is because he was very, very concise in all of his proofs. What usually would take most professors a full day to write or proof, like a full paragraph or like a full page of work to show the proof, he was able to write in a paragraph. So he was very, very concise in his proofs. It was beautiful. And so I bring this up only to say that his proof of the inverse function theorem took up 3 pages. So it took us 2 days of class time to prove it. It's a very, very difficult proof, but very, very cool. And I say that just to once again kind of build up Leibniz as why he was way cooler than Newton. Because if you think about it in terms of differentials, it actually makes sense. dy dx is the derivative of the function. Dx dy would be the derivative of the inverse. So dy dx, if you wanted to, so well, let's actually say dx dy, you could rewrite that as 1 over dy dx, because flip the fraction. So that's exactly what this is. The inverse's derivative, for the people watching the recording, the inverse's derivative is equal to 1 over the derivative. Fascinating. Leibniz, like the rest of Europe, was able to figure it much quicker because of that thought. That's not 100% true, once again, because dy dx is not actually a fraction, as you'll find out in 283 and beyond. But you can think of it in a lot of circumstances, and that allowed them to figure this out. And then once they started dealing with multivariable functions and realizing that differentials weren't actually, or dy dx wasn't actually a fraction, they knew that it was true, so they were able to figure out they knew it was true, so that helped them figure out how to prove it for multivariable case. So super fascinating in my opinion, and just very, very cool. So with this one, you'll notice if we look at this section, I only have one question on the inverse function theorem. I promise you I will not bust this out. There's no, they're like not on your quizzes, not on your exams, because this is a highly theoretical thing. The main reason why we talk about it is to talk about the derivatives of inverse trig. But in fact, do we have time? It's 10:08. And let me look at our schedule. We're supposed to go over 2.6. I'd rather spend 2 days on 2.7. Because 2.7 is related rates, which students seem to not like. But they're wrong. It's a really fun section. Related rates is word problems. So we're all excited, right? Word problems. I'm glad we agree. Cool, cool. You gotta have them. You gotta have them in a math course. You gotta have some word problems. It's kind of a hazing ritual, but we can do this one. So find f inverse of f inverse prime of -3 if f of x equals x squared minus 4x minus 3 with a domain of 2, to positive infinity. So if we wanted to do this, the fact of the matter is we could find the derivative, or we could find the inverse function if we really wanted to. You'd have to complete the square and then solve, but I don't recommend doing that. But instead, what we can do is this is our b value. So from here, that means that b is equal to -3. We need a. We need a to use the formula. That formula. Because f inverse of b, f inverse prime of b is equal to 1 over f prime of a. So the thing is, we know what b is. And remember, f of a is equal to b. So f of a is equal to b, which implies that a squared minus 4a minus 3 is equal to -3. Which is weird. Let's digest it one more time. I like, even though we're not going to do this, I think this is a very, very good practice in breaking down the logic of what we're trying to do. We know what B is because we're trying to find F inverse prime of -3. That is our B value. In order to compute it, we need we need A, because that's how we're gonna find F prime. So F of A is equal to B. That's what we need, like, that's what we're trying to find. We have B, we need A. So we're gonna plug in A into the function and solve for it when it equals B. So that will be A squared minus 4A is equal to 0. That gives us A times A minus 4 is equal to 0. That gives us A equals 0 and 4. Oh no, we have two A values. Which one? Remember, A is an X value. 4, because the domain is 2 to positive infinity. Because the domain is 2 to positive infinity, we don't include the 4. We don't include the 0, excuse me. So that's our A value. 0 is not in the domain. Now, we've got our A value, we've got our B value, we've got F, we don't have F inverse prime, but we don't need it, but we still need F prime. F prime of X would be 2X minus 4. So, by inverse function theorem, oh man, it's been ages since I've written it out. I always like, after a while, and like you do mention it several times in upper division mathematics, and to save yourself, you use you write IVT, inverse function theorem, IVT. But the problem is there's also a theorem called the implicit function theorem. So there's another IVT. So you do INVT and IMVT. But either way, by the inverse function theorem, F inverse prime of -3 is equal to 1 over F prime of 4, which would be 1 over 2 times 4 minus 4, which would be 1/4. So once again, the utility of this theorem is that it allows us to find tangent lines and rates of change of an inverse function without ever having to find the inverse. That is very, very useful, quote unquote, useful's maybe being generous. But from a mathematical standpoint, that allows us to solve problems that could not be solved, which is a big deal in mathematics. We love being able to solve problems. So, anywho, once again, do not worry about this. You're not going to be tested on the inverse function theorem. You do not have to have it memorized. There's not going to be any questions on it, whether it not on a quiz, not on an exam. What is fair game are the derivatives of the inverse functions. So sine inverse, cosine inverse, tangent inverse, cotangent inverse, secant inverse, and cosecant inverse. Those things are all important derivatives. Now, the one thing I will tell you, I don't need you to memorize, so don't memorize these ones. You only need to memorize the other two, the other 4. The reason why I said the other 2 is because you'll notice that they're very similar. The only difference is that the co-functions have a minus sign. That's the only difference. The derivative of sine inverse is 1 over the square root of 1 minus x squared, whereas the derivative of cosine inverse is -1 over the square root of 1 minus x squared. So they're basically the same thing. And they follow the beauty, once again, the beauty of trig strikes again. Of course it is that it's symmetric and beautiful, and that the co-functions still, even the regular co-functions have the negative sign, and the inverse co-functions have the negative sign. So the co-functions have the negative sign. Now, if you want to see the proof of these ones, it requires implicit differentiation primarily. And I'm happy to show you if we have time at the end, maybe we can bust out one of the proofs just to have some fun. But for right now, I just want you I want you to realize, like, accept, but I can happily prove it to you either before class, after class, or in office hours, or whatever. A proof of these theorems, the proof of these formulas. So find, like, so now we just have 4 more derivatives, technically 6 more, but I don't need you to memorize the other 2, the E and F. I don't need you to memorize them because they're so weird. That's like the weirdest derivative rule that we have. I don't like it. I don't think it looks pretty. Yeah, I know what you might be thinking. Well, like, hold on a second. It's pretty nice. Hold on a second. Okay, I need to, that is fair. That is 100% true. Sorry, I went off on a tangent. Jokes. Oh God. I love Trig. Trig has way too many jokes. Okay, so suffice to say, now we have a bunch of different derivatives that we can now do. We can do more derivatives, which is what we always want to do. So sine inverse of t squared, find the derivative. So sine inverse's derivative is 1 over the square root of 1 minus x squared. So this is a chain rule. Because it's not sine inverse of t, it's sine inverse of t squared. So it's the derivative of the outside, evaluated the inside. So f prime of t would be 1 over the square root of 1 minus x squared. But because it's a chain rule, it's not x squared, it's t squared squared. Times the derivative. I'm going to write this one out in full detail this time, just because it's new. But in the future, we'll kind of skip that step. So it's the original derivative would be 1 over the square root of 1 minus x squared, but this is not sine inverse of t, it's sine inverse of t squared. That's why it's t squared squared. And so at the end of the day, f prime of t will be 2t divided by the square root of 1 minus t to the 4th. Inverse trig will have a decent role in 182, specifically with integration, which we'll get there at the end of the semester. But these things do come back. This one definitely to kind of throw you off a little bit. There's an inverse tangent and a regular tangent. So, what else we got? Okay. Cool. Ah, yes. No problem. All right. Let's find the derivative. The first one's going to require a product rule. This is your f, and this is your g. The second piece will not require one because it's just a product of, it's a constant, not a product, really. So h prime of x. I'm going to put the first term's derivative in brackets so that we know that's the derivative of the first term. So f prime be 1 times g tangent inverse of 2x plus g prime. The derivative of tangent inverse is 1 over 1 plus x squared. So it'll be 1 over 1 plus 2x squared times 2 times x. Make sure you understand where that's coming from. I'll explain more. I'll explain it again once you've written it down so we can fully grasp it. I always feel like inverse functions are one of those things where like you like with an essay or something like that, you read the same sentence like a million times trying to decipher it. Like you really have to break it down word by word to finally understand it. So I feel like with inverse functions, because it's like you gotta f of a equals b, so that means the f inverse of b equals a, blah, 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 but I do love inverses though, it's fun. So the reason why the derivative of tangent inverse of 2x was this is that the original derivative of tangent is 1 over 1 plus x squared, but this is a chain rule. So it's 1 over 1 plus the inside squared, so 1 plus 2x squared, times the derivative of the inside. The derivative of 2x is 2, and so that's where that's coming from. And then the minus 1/4. The derivative of tangent is secant squared, evaluated the inside, so 1 plus 4x squared times 8x by the chain rule. And you can leave it as is, or we can write it prettier. And I'm going to write it prettier just because I think this one's a little bit daunting. But on an exam, you do not need to simplify. So that'll be tangent inverse of 2x plus 2x over 1 plus 4x squared minus 2x secant squared of 1 plus 4x squared. Any questions on that? So yes, it does feel a little daunting right now just because you don't have these ones, you haven't practiced them at all. But all the rules still work. It's the good thing. We can still do implicit differentiation. Wait. Did I not? Is the next one the implicit differentiation problem? No. There we go. There's the implicit differentiation problem. All right. So this one, I don't know why it's such a look at my notes. Like all that room for that problem. It's like way too much room. It doesn't require that much work. So that's F. That's G. So F prime is 1 over the absolute value of x times the square root of x squared minus 1. Legitimately, I barely have that one memorized. I barely have the secant. I can tell you definitively, like in my entire mathematical career, I have never used secant inverse in anything. The only time I have used secant inverse is teaching it, 100%. So that is why I don't want you to have it memorized. That is a non-useful function. Nobody ever uses secant inverse. Yes.
All three.
How do you mean?
The only thing was we're trying to find. The log, I think, with LN.
Oh, the logarithmic differentiation stuff. We could use it, but it's not going to be needed here. Yeah. But all the other rules like product rule, quotient rule stuff, those things are still all valid. So G prime is 3x squared e to the x cubed plus 1. I'm just writing it so that the polynomial piece is in front. You could easily write it as e to the x cubed plus 1 times 3x squared, but either way. So dy dx is equal to f prime, so 1 over the absolute value of x square root of x squared minus 1 times g e to the x cubed plus 1 minus g prime, so 3x squared e to the x cubed plus 1 times secant inverse of x, all divided by e to the x cubed plus 1 squared. And we can leave it like that because we don't need to simplify it or use it for anything. Any questions on that? Good? Okay. So then the next one, find the equation of the tangent line of p of x equals 6 x cosine inverse of x minus 1 when x is equal to 1. All right. All right. This one has a fun slope. Just trust the process. Even though the numbers are weird, I'm weird. I'm still here. So we can handle it. So slope. If we're finding a tangent line, we need slope and we need a point. We don't have either yet. So to get the slope, we need to take the derivative. So p prime of x would be, so we need to do a product rules, f and g. F prime is 6 cosine inverse of x minus 1 plus g prime, which is -1 over the square root of 1 minus x minus 1 squared times 1. I'm writing the times 1. It's not necessary, but I'm writing it to remind us that this is a chain rule. It is a chain rule. Cosine inverse of x minus 1. You have to do a chain rule, but the derivative of x minus 1 is just 1. So it's unnecessary to write it. And then times 6x. All right. So from here, we'll plug it in. P prime of 1 will be 6 times cosine inverse of 1 minus 1, which I'm just going to write as 0. Let's just write 0. Plus 6 times 1, negative 6 times 1 over 1 square root of 1 minus 0 squared. Right? All right, what's cosine inverse of 0? All right, hint. So cosine inverse of 0 equals a theta, because inverse functions, trig functions taking an angle spit out a number. Inverse trig taking a number and spit out an angle. So you're asking yourself, when does cosine of theta equal 0? And then the other thing you got to remember is that cosine inverse is defined from 0 to pi. So the answer should be not 0, because that's when sine is equal to 0, pi over 2. You also have a calculator, by the way. So this is pi over 2. So what we end up with is 3 pi minus 6. Ah, yes, the great slope of 3 pi minus 6, m tan. Perfect. Beautiful. Hey, it's just a number. So for the point, P of 1 should equal 6 times 1 times cosine inverse of 1 minus 1. I'm writing it in explicit detail, so we see in our notes that I'm plugging it into the original function. On an exam, you could just write down what the answer is, and I'm fine with that. But that will be 6 times cosine inverse of 0. So that will be 6 times pi over 2, which is 3 pi. All right. We have the point 1 comma 3 pi. Beautiful tangent line. Are you guys ready? This is another reason why I like slope intercept form, point slope form more. Because now it's y minus 3 pi equals 3 pi minus 6 times x minus 1. And we can keep it like that. Unless, of course, you guys want to solve it. You guys want to solve for y. All right, we can. So that'll be on the side, y equals 3 pi minus 6 times x minus 3 pi plus 6 plus 3 pi. So what I'm doing, just in case you're curious, I distributed the 3 pi minus 6 into both terms. So that's why I got the 3 pi minus 6 times x. Then distribute into the -1, that becomes a negative 3 pi, and then plus a 6 because it's -6 times -1. And then I added the 3 pi, that cancels. So we get y equals 3 pi minus 6x plus 6. If you really want to do it in that way.
You know that feeling when your kid says no?
Yeah. Right now, I never really minded the no stage. The Y stage has been, it's beautiful, but also terrible. We need to get going. Why? What's gonna happen if we don't? Why? Like, he loves asking those two questions, and those two questions are kind of inverses of each other, so it becomes an endless loop. So he's testing his concept of recursion right now.
Like that repeat, get the one, you know, that whole thing.
Yeah. Speaking of which, now that I mentioned repeat. Silliest thing, because it's important for you guys to know this. There's a reptile zoo in Washington. Super important for you guys to know. I know. There's a special reptile zoo. They have a bunch of really cool things. They have an albino alligator, and a bunch of other things. But one of the coolest things that they had was a two-headed turtle. And they named the two-headed turtle Pete and Repeat. It's hilarious. Absolutely loved it. Anyways, super important to bring that up, I know. Now you have that piece of trivia. So any questions on that? Yes, the numbers are weird, but plenty of numbers are weird. So it's okay. You can leave it as is. Totally fine to do so. All right, last one is you can still do implicit differentiation with all this stuff. So we're gonna ddx both sides. Derivative of sine inverse. This is where I'm going to take a little bit of a slow step, and I'm going to write more details. So sine inverse's derivative is 1 over the square root of 1 minus x squared. So it's going to be 1 over the square root of 1 minus xy squared times the derivative of xy. I'm doing it in steps because this is kind of weird when we're first saying we're taking a chain rule with a product rule on the inside, but the product rule is with x's and y's. Good news is that the other half, the 2/3 tangent inverse of 4x, there's no y's in there, so there's no product rules. It's just one chain rule. So that'll equal 2/3 times tangent inverse's derivative, which is 1 over 1 plus x squared. But since it's tangent inverse of 4x, that's 1 over 1 plus 4x quantity squared times the derivative of 4x, which should be 4. So this is f, this is g. So it's going to be 1 over the square root of 1 minus x squared y squared times f prime. So 1 times g y plus g prime. So that's dy dx times f, which is x, equals 8 over 3 times 1 plus 16x squared. Any questions so far? It's okay if there are. Yeah. We got to do a little bit of chain rule stuff here. Now, how we solve this one is completely up to you. One option would be to FOIL in or distribute in that thing and then solve like we normally do. But a clever way would be to multiply both sides by that square root of 1 minus x squared y squared from the start. Either way is fine. Do you guys have a preference? Yeah, multiply, like that's what I would recommend. So I'm going to multiply both sides by that value so that it cancels it here, and then I should write on the left, but not going to. And so we get y plus x dy dx is equal to 8 square root of 1 minus x squared y squared divided by. Do you want us to distribute it in the 3 or just leave it? Leave it. I agree. And then we'll subtract y from both sides and divide by x to get our final answer, which is that dy dx is equal to 8 square root of 1 minus x squared y squared over 3 times 1 plus 16x squared minus y, all divided by x. And we can leave it like that. Or we can simplify it if we want to, but we're not asked to. We're just asked to find dy dx. So tell the person that you can simplify it if you want. It's a DIY derivative. Any questions on that? All right. Well, we are ahead of schedule, which is news to me. I'm never ahead of schedule. We could either start up 2.7, like we're gonna have, it's crazy. We have 2 days. What am I gonna do? What am I gonna do with 2 days on related rates? Oh my God, we're gonna get to so many. Our rates are gonna be so related, it's gonna be ridiculous. I'll make a crossword on it. Have volume, area, all those things. What? Tiers as well. It's related rates are definitely, I'm not trying to scare you guys at all. I really like, they are intimidating, like, and I will say when I first learned them from my original professor, my really original teacher, Mr. Kelartinian, it was really hard for me. The way he presented it did not really make sense to me, because related rates are one of those things, there's a lot of moving parts and it becomes overwhelming very quickly. But in college, I got my teacher, Dr. Jennifer Taggart, and she had a way of describing it that was beautiful. It was very, very well organized, and I think that's going to help us a lot here. So that'll be it for today. If you'd like me to prove one of the trig functions, I can, but otherwise, maybe take a break. All right. All right. Perfect. I like that. I like that. Thank you guys for being so kind. Yes.
On the next page, which one do we not have to memorize?
Excellent question. So that's a fair thing. So I'm going to highlight them in red, any of the ones that you do not need to have memorized. You do not need to have memorized this one. Phil, is that really the good use of time right now? Yes. So that one does not need to be memorized. That one does not need to be memorized. This one does not need to be memorized. And this one does not need to be memorized. All others are fair game. Let me just make sure. Yes, all others are fair game. So those 4 are the ones that you do not need to have memorized. And yeah, all right, guys. That'll do it for today. If you guys have any questions, feel free to email me. Otherwise, I hope you guys saw in my email that office hours are canceled today. So sorry about that. If you were planning to come over, you can always email me. Otherwise, you guys have a great rest of your day and a great weekend.